Okay, good to hear. Hopefully people can see my screen. Yes.
Yes, sir.
Okay, cool. So last time we were looking at GRUs, right? And hopefully people are okay with what GRUs do, right? And how the gated aspect of the recurrent units help in, you know, weighting things from the past, as well as gating how new information is being combined with the past information. Now LSTMs pretty much do the same thing, but they are a little bit more complicated. And uh, I'd like to give credit to one of my advisors, Mike X Cohen here, right? Most of this stuff is from his deep, deep understanding of deep learning lectures, and it's laid out very nicely there if you want to look at it as well. But what are LSTMs, right? What is long short term memory? Any idea what that means? Anybody? Do you know what long short term memory means?
Yeah, so here we are trying that whatever inputs we are getting, we
Mhm.
maintain it for a longer period.
Longer period of time. Yeah, exactly. So there is some long aspect of the memory in addition to some short term memory, right? Like, because we were looking at previously just RNNs, where the point was that after a series of recurrent passing through the recurrent network, you see that the memory of the long term past kind of diminishes, and only recent past gets embedded in there. So in some sense we need to keep hold of this long term memory, or we need to keep hold of this past, right? Now what is the limitation of, say for instance, why can't you hold on to things that are back in the past for a long period of time? What is the shortcoming there? What is the thing that's missing in the previous networks, or at least the previous recurrent neural architectures that we saw, that we could address? What is the issue? Anybody? Why is it that we are not able to hold on to long stuff?
So because of the vanishing gradient.
Yeah, and another one is
Hmm.
there is no
Hmm.
memory.
Memory, yeah, yeah. In some sense,
Complexity.
yeah. Uh, Complexity, I don't know in what sense complexity. The
Like
idea,
LST,
sorry, come again.
yeah, like LSTM have a more complex architecture
Architecture, yeah,
than
yeah, that's true, but the complexity doesn't give rise to the long short term aspect, right? It's more
okay.
that it is complex, but the point is what needs to be done in order to have a long term memory, right? Like for example, if you have a fixed memory resource, right, and you are dumping everything into it, that at some point you might have to get rid of something in order to store something, right? Yeah,
Hmm.
so that sort of stuff happens because if you think about limited memory capacity and the limited nature of memory resource, you should the now natural intuition is you have to forget something in order to remember something, right? Because you have limited resources to play with. Now the idea of long term memory is if you have to store something for a long period of time, then whatever that's coming that is immediate or in the immediate past needs to be forgotten in some sense, right? Or at least part of it needs to be forgotten, or part of it which is irrelevant needs to be dropped off, so that something that's more long term and more relevant can stay there in the memory of the network or in some memory resource for a long period of time, and whatever is actually important gets added to it and gets weighted in some sort of a fashion in order to give you this long-term memory trace, right? And that's the idea of an LSTM. And in terms of the equations and the architecture, it's a bit complicated. So we look at it one by one, and it's very similar to the GRUs, and that's why I introduced them earlier, because there are also gates here, right? There are many types of gates, but the architecture and how these components combine with each other is different, right? But in terms of the math, everything is the same. There is no difference in the math. It's just that you're taking some weights, multiplying it some activations or some inputs, and then passing it through a sigmoidal activation function or a Tanich activation function. So the math is pretty much the same. There's no change in how the math is applied in different places, but the idea of how these components interact with each other, that's the difference between, say, a normal RNN or a GRU and an LSTM. Okay, so there are three inputs to the LSTM. If you look at it, one is the input sequence that you're providing. The other is the previous hidden state that's coming in, and there is something called as the cell state. Okay, in an LSTM, the cell state can be thought of as this long-term memory state that the LSTM holds, right? So there is something that's more short-term and immediate, that is this H of t, which is influenced by your input. And then there is some long-term input, which through some gates gets modified, and that trace is also maintained. Okay, and in some sense, the long-term memory can also affect what is going on currently. Okay, so that's basically it. So there are two parallel streams of information. One is influenced by your input and your previous history, and it gets updated. And then there is something much more long term, that is what's called the cell state, and that also travels parallelly, influencing the current representations. That's basically the entire idea of an LSTM. So we look at each of these gates one by one, okay, and what they actually do. All right. Any questions here? People are okay? All right.
Sir,
Yeah.
what is basically a cell is?
A cell state is nothing but another type of activations, right? Other type of a hidden state, or this hidden, in this case, we call this H, but we give this a different name basically. It's another type of hidden state, but how it is actually realized is slightly different compared to the other cases, right? How that combines with each other. So that's different. But in essence, everything is activations basically. It's a combination of weights multiplied by some inputs and multiplied by some previous inputs or the current input, and weighted by a nonlinear activation function.
So
So
what is that component which is actually giving it a difference as compared to the normal RNA?
the
Cell state only.
the cell state, right? And then the gates and how they interact with each other, because in GRUs also we saw gates, but the gates were being applied in a slightly different manner, right? There weren't so many gates, and the architecture wasn't so complex or so intricate, but still was achieving some level of balance between how previous information and current information is balanced in the network. This is a more extreme version of that, if you can think about it. Okay, so as we go one gate at a time, you'll try and understand the idea behind why the cell state and what information it could it possibly carry, and what happens through these gates. So we'll have a look at each of them. Okay.
Yeah, sir. Before going to the each of the state, can you just explain how
Mhm.
these components are interacting overally? Like we see four different layers are there, correct? So
Yeah.
W1, WI. So who
So
is
these are all weights. So if you imagine, right, this is probably the part of the network that is for a simple RNN, right? Typically, that is, you take the previous and the current previous states, hidden states, and the current input, pass it through some weights through a nonlinear activation function, you get your output G and the next hidden state, right? Now in that we have several components, right? We have several types of different gates that interact with each other to kind of give you this long-term memory trace, and how that influences your current information also is embedded in here, right? If you look at it one by one, I'm pretty sure you will be able to understand it, right? So before we
yeah?
even pick apart, look at it as a whole, it's easy to kind of reduce it and pick it apart. So hopefully
Yeah,
that
sure.
will make it clear. Yeah. So the first thing is the forget gate. Okay. So what it is nothing but if you take some weights and you take your input and your previous hidden state, xt and ht minus 1, and then you pass it through a sigmoid. So this is a gate because you're passing it through a sigmoid function. So the variables in f will be either close to 0 or it will be close to 1 in some sense, right? That will weight information between what is happening in the previous time step and how the current input is being combined. And what it influences is this previous cell state. Okay. So it combines your current input and your previous hidden states. And the idea of this gate is to determine which of the previous data to forget and which to remember, right? Now, the idea that I told you before, in order to keep a long-term memory information, you need to drop some current information, right? Now, this gate decides which such current information to drop, okay? And that's done through training, obviously, but these weights then decide whether the current input information is worth storing in the long-term storage because that has some relevance or not. For example, if I have some word where or some sentence where the word the comes or the word a comes, right? Maybe this is not too relevant to keep. Forget this information of the current input, for instance. Okay. And then maybe if there is a word which is something like cow or something, right? Right, maybe this verb or this noun is very important, or this word is very important because it has some relevance to something that's going to happen in the future or something that has happened in the past, so you need to remember it, for instance, right? So this gate decides and tells or influences the cell gate here, right? Because there's a multiplication sign here, so I'll tell you how this gate interacts with it, but there is this gate decides which information from the previous hidden state and the current input to actually forget and which to remember. That's basically what this gate does. So that's often why it's called the forget gate. All right. Now, if I move on and talk about this next gate, which is the input gate, right? Mathematically, it's the same thing. It's taking a bunch of weights. It's weighting the current input and the previous hidden state again and passing it through a nonlinear sigmoid function. So the reason it's called a gate. And this time what it's doing is it's not influencing the cell state directly. It is influencing your current activations. That is, it's combining your current input and previous states and decides which current samples. Very important to understand. That is, this particular pathway that you can see, which goes from here to here, determines the current activations of the neural network. And this gate influences the current activations and sees and tells the long-term trace, or in some way it gets added on to the long-term trace to tell which of the current information to actually keep hold of, right? So in some sense, this part tells you which information to actually forget, whereas this part tells you which information to actually remember after you take your information and pass it through some activations. Okay. So this transformation that happens tells you about what activations are very likely important. This tells you how to weight them and then get added into your current cell state, or sorry, to the previous cell state. So the long-term memory trace has a combination of which things to forget or drop from the current information and which things to add after some transformation into the long-term storage. That's about it. Okay. So that's what this input gate does. All right. In that sense, if you look at this particular trace, this is often what's called the cell gate. Okay, so the word gate here is pretty misleading, but in literature, that's how it's named, because this is a tanh function, not a sigmoid function. But I mean, I don't know why they called it a gate. But anyways, this is often also it's basically you take your current input and your previous information and get representations. This is not technically a gate, but it's more about activations or representations, right? Because the values here will lie between -1 and 1 in this case. So you get a weighted combination of that and you pass through it. So this is where your input gates get influenced, right? Your I gate influences this G, which then gets added onto your current, sorry, your previous cell state. Okay. So the point is that there are 3 stages here, as you can see, of the how the input is being modulated in order to change the cell state. First thing is you are deciding which things to forget or drop from your input, which things to actually remember after you transform the input, right? And that is getting multiplied and added to your previous cell state to get your current cell state. That's about it. Okay. Any questions till now? Anybody has some queries?
So one basic question, like
Yeah.
what is like why we are selecting multiplication addition to things? Is any impact of
Yes, there
with
is.
both as the multiplication?
Yes, there is. We'll look at it when I go to and discuss how the previous cell state becomes the current cell state. You will understand how this multiplication and addition actually gets influenced, right? In this diagram, it's just there for representation purpose, but when I show you the math behind it, you will understand what it actually does. Okay, so we'll look at it in just a couple of slides.
Okay.
Okay. Any other questions? The idea of a forget gate and an input gate should be pretty intuitive, right? What to forget, what to actually add. That's about it.
And sir, what is for W0 that?
Yeah, so then the next thing is that we'll look at it next.
Okay.
Yeah. Till here. All right. So if this part is done, now we need to talk about this output. That is, this ht minus 1 and xt through this connection is becoming the next hidden state ht. But there seems to be another gate here. And what is that gate? It's often what's called the output gate. Okay. Now, what the output gate does, it then basically, again, the computations are the same. It's the weights are what is going to be different, right? In each of these cases, you can imagine WF will be different from WO because you need to decide what to forget, and that might be different from what to send out, and that might be different from what to actually remember, and so on and so forth. And that's what the network is trying to figure out, right? What things to forget, what things to keep, what things to send out to the next step. And this is what the weights are getting tuned to in order to perform that sequence-based task. All right, got it? So now what this output gate is doing is it's basically, again, combining your current input and your previous output. Sorry, your current input and your previous hidden state, and then weighting it. And this time, this O of t, what this is this intermediate output after this, right? Now, how this O of t is influencing H of t, we'll look at it in the next slide, because you can see this information that's coming to H of t from C of t. So there is an information that's going from here and flowing here, right? So what this tells you is about how the actual cell state, which is holding the long-term memory, is influencing your next hidden state. Okay, and this O is actually weighting how much of that cell state to get influenced to the next hidden state. So for instance, I'll just show you. The next hidden state is O of t times tan h of C of t, right? So this information is then pushed through an activation for something like a tan h, and then it gets weighted by this O. The O weight, basically when O is multiplied by tan h, it will switch off certain activations, it will switch on certain activations, and those combine to give you the next hidden state. So at the end of the day, the hidden state is nothing but a combination of something from the previous, which is the short-term memory, and something from the long-term memory, right? A part of the short-term memory is there, a part of the long-term memory is there, and both of them are sort of represented at the current given state. the next hidden state. All
The
right.
short term memory means HT minus 1.
HT minus 1. So this is your short term, right? This is being influenced one step after the other just by what is happening in the previous sequences of inputs, right? But this is
Term means time
something
duration,
that,
right?
sorry.
Sorry, just a general question. Short
Yeah.
term means short time duration, right?
Short time
Or
duration. Yeah. Short term is something that's seen in the recent past and not something that's way back in the past. Now, recent past and way back in the past are subjective, but in a sentence, for example, a few words or a couple of words or a couple of tens of words in a sentence could be short term. But if you have to remember something from like a few paragraphs ago, right? And that's probably long term. Right? It could be thought about it like that. All right. So this is your short term in some sense. This is the long term memory trace. And the long term then influences the short term part. That is, okay, next time when you come, you keep also you have some information about what's happening in the long term context, right? And so on, so forth, right? So it's basically, again, combination of the previous hidden states and your current input and newly current cell state. So this is your current cell state that has come out, and that's passed through this tanh and weighted with this O of t to give you H of t. All right. So that's your next hidden state, which will then come and then go back here, right, for the next iteration. And finally, this is the cell state, and this is pretty much intuitive, is because what it combines first is your previous cell state gets multiplied by this forget gate. That means whatever in the previous cell state that was irrelevant or something that's relevant, could also be thought about, that will get remembered and the rest will get forgotten, right? So those that get multiplied by 0 here will get pushed down, and those that multiplied by 1 will stay, right? So that basically preserves some of the long-term storage. And then the new information I of t and this G of t, which is basically the current activations, right? So these two combine and then they get added to the current cell state to produce the new cell state. So you have something from the present, you forget something about the past, and you keep a record of that. That's basically what an LSTM does, right? And because it keeps a record of this and influences your current information, you have a trace of both the long and the short-term memory. Thereby, you can make decisions based upon things that even happened quite a bit back in the past, also with respect to the recent present. And that's what makes these really powerful in some sense. Okay, so you remember the previous cell state and you add some of the current cells. So I of t into G of t gives you the adds to give you what's to remember or what sort of new information to add, and this tells you what old information to forget. Okay.
So basically, this WF actually, leading to cancellations, already learned stuff, a little bit already learned stuff that is coming from the C T minus one. But then we determine we don't need this because of the new context. So you're
Yeah.
forgetting that the multiplication is to nullifying those learned stuff.
And not learn stuff, those stuff that can be irrelevant for the current context, right? I mean, so if, for example, if you have certain words that you don't have to keep them in the long term memory storage, right, they are not relevant for the final objective of the task, for instance, then they should be dropped, and the WF learns that, right? So the WF weights learn that, right? Like whenever you see a certain representation here, then when they combine, you see that the output becomes minimal for those representations. So when you multiply those with the the previous cell state, those representations do not get amplified; they get suppressed.
Suppressed, yes.
Yes, the ones that are actually needed will get active, because if this is 0 or 1, right? The ones where it is 1, those activations will still remain in CT minus 1. those where are zeros, those activations will be suppressed. And then you have your new information that's coming in, right? WG will decide what new information comes in, how should it be represented. WI decides what aspect of the new information should be taken to the long-term storage, and that forms your new cell state CF. Okay. Yeah, it is a little bit complicated. I understand the architecture isn't simple. And by the way, as I mentioned before, this is not an architecture that they came up on the spot. That is, they did not come up with such an architecture, just laid it out and said, okay, this is it, right? These came with a lot of iterations, lot of testing of different ways in which these gates would interact. In fact, there is a lot of ideas now where people are trying to come up with interesting new gates. You can imagine you can even drop this I gate and use inverse of this F gate. I'm just putting it as F inverse, right? Now here it tells you what to forget. If you take an inverse of it, it will tell you what to remember, right? So the same gate can be applied to both the ideas, and this will reduce the number of parameters that you want to train, right? So you don't have to train a WI, you only have to train WF, for example. And that will reduce the number of parameters that you have to train, and that might make the model much more simpler and easier to work with. Right? Yeah. So people have experimented a lot with this, and finally, this is the architecture that seems to work really well with sequences, and that's what comes into courses, and that's what comes into practice. But that's why it's a evolving field, right? This doesn't stay static. Right, like what you learn here, if you go and look at the recent work, this would have been modified to do something much more better than what it is doing now. Right?
So like WG, right? What is the role of the WG here?
WG will just take your current input and previous hidden states to give you some current activations, right? This is passed through some TANH. So this, you should think of it like this is your in the way in which some memory is being represented in the brain, right? Or in this brain of this LSTM, for example, right? So this is where your memories are being transformed, non-linearly transformed into something that holds some information about the current and the previous state. To that, you add this gate and tell it that, okay, in these representations, remember some of them, drop some of the others, and add it to the new cell state.
Okay.
That's what it means. Okay.
It's another another part of memory, like that.
Exactly. So the point is that the more weights you add, the more complicated behavior the network will start to exhibit. But the flip side is, the more you have to train the network, that means you need to have more data to train the network, more rich data. Otherwise, the weights will not get trained, and you will not.
This means like we can add W, G1, G2 like that many gates with some.
Yeah, absolutely. In fact, that's what I'm telling you, right? Like people who have experimented a lot with this. In fact, you could possibly think of adding another thing here, right? As you say, right? I can add another TANH with a WG2, as you say, and then I can do a G2, and this time, I can instead of adding it, I could do something else here, right? And this time I could subtract, and instead of using this gate, I use these combination and say that I'm learning WG1 and G2. G1 is telling what to remember, G2 is telling what to forget, right? So you could use combinations of these. There could be many ways in which this could be modified. Maybe that gives you a better performance on specific types of sequences, right? In fact, most of the time, it's the data that should drive what sort of model to use, right? So when people do these sorts of research, the intuition comes from, okay, if there's a data that has some sort of an underlying structure like this, I need to have a network which can probably remember some aspects of this data for a long period and some parts for a short period of time. And that's where this architecture then evolved, right? And most of the time that is the case, right? It depends on the end problem that you're trying to solve.
Sir, in terms of the TANH activation WG,
Yeah.
that also has a role of either activating certain things and keeping other things deactivated.
Right. But it doesn't push them to zero in some sense, right? So that's the point. It's not getting suppressed. It's just that it's these are you can think of them as they are some representations in a much more richer dynamic state, right? Like It's not something that's as simple as zeros and ones. And most of the times, if you see the gates get multiplied, right? Whereas the activations get added, right? So if you can see that difference, it's subtle, but it's very important, right? So you can see here the gates get multiplied. So it tells you whether certain things have to go down to zero or certain things have to stay the same, right? But when it comes to activations, they get added to it, right? Same way, the activations get added, right? The weights or the gates get multiplied. So there's a difference there, if you see about it. So activations tell you about some sort of a richer dynamical representation of that memory. The gates tell you which to keep and which not to keep, basically.
Okay, and sigma there is the symbol, or that actually means sigmoid?
The sigmoid function. It's not it's the sigmoid function, right?
Okay.
As we discussed. This is
Okay.
okay. All right, guys. So that's about it for LSTM. So to kind of summarize it, what you are doing, 4 operations that you are doing with an LSTM. You are forgetting the past. Right? You're forgetting the past. You are remembering the present. That means it's a combination of this and this. Right? You're using these 2 things. You are remembering the present. That is, or you're deciding what to remember about the present. Okay. Then you're planning for the future. Right? That is, you're using this to decide how much things that I have to keep for the future. And you're keeping a record of the history. Right? So that's basically the simplest architecture of an LSTM, the basic unit. Right? You are planning in such a way that you're forgetting the past, remembering the present, planning, and then recording.
I
That's
have a question. When we talk
Yeah.
about keeping a record of a history,
it.
what is the duration of this history? We can say that, okay,
Yeah,
this much-
very good question. No, absolutely. Really nice question, right? That depends upon the type of task you want to solve, right? Sometimes there might be certain things that and as I said, right, the recent past and way back in the past is kind of subjective. It depends, right? Like for a few sequence histories, like for example sentences which are because you tokenize them typically when you give these to the model, right? So there might be certain number of tokens that you can give, and how much number of tokens that it can look or use in the past, that depends. So it's mostly in practice that you understand or get this intuition. I can't give you like an exact number, right? Like I can't tell you, okay, 1,000 tokens in the past that it can remember or something like that, but it can do better than what an RNN would do, right? So for example, if an RNN can take into information of a few sequences or a few words in the past, right? This could be able to do much better than that. That's the point. Okay. But I don't think, if I can find it out exactly if that's there, I'll let you know. But typically you can't put a number on it. It's more like what the current problem actually requires, right? Like maybe the current problem requires the LSTM to remember say 10 or 15 or 20 tokens back in the past, for example. That's enough, right? And so the network and the weights will train in such a way that that's how the problem will be optimized. But it'll give you the luxury of having such a architecture that can do that. That's the idea. Okay. All right. So I think we'll end it today, guys. I went a little bit over, but I thought we should at least look into this today, because tomorrow we can start looking at some of the DNN optimization and regularization. But quickly, I think we can stop it today. It's fine. Yeah, let's end it here. We'll summarize it tomorrow. Any questions?
Sir, yes, sir. Sir, what kind of questions can we expect in these cases? Like, for example, you gave an intuition type of questions in this class test. So will be there an architecture based question, or?
Yeah, I could ask you something like, okay, so okay, I can't think of it at the top of my head, but I could ask you something like, if I drop some of these gates, right? Yeah. So what aspect of the LSTM are you actually losing? What functionality of the LSTM are you getting rid of, or are you losing? If I add something, what are you gaining, right? That tests how you understand this network and how much you have internalized this architecture and have an intuition of how it works. So it's important to get that. So it'll be questions like that, right? And because it's hard to test concepts in these unless you actually work with them, but it'll be questions like this. Okay? Now, for example, I might ask you, if I cut this out, right? What will happen if I ask you this question? So if I don't take a long-term memory trace,
Then it will behave like a GRU network.
yeah,
almost.
absolutely, exactly, very nice, superb. Yeah, it'll behave almost like a GRU because it still has a gate in it to tell you what to drop and what to keep, right? But yeah, that's very nice. Yeah, cool. So that's basically it, right? So this tests your idea of how much you have an understanding of this sort of a network. Cool. Anything else? Okay, guys, then thank you for your time and your attention, right? And I'll stop the recording now.
Thank you all.
Thank you, sir.
Thank you. See you guys tomorrow then.
Thank you.
See you.